Assalamu alaikum and welcome to the second part of our lecture number 4. In the first part, we did some review of Fourier analysis, continuous time Fourier analysis rather, and we saw some Fourier series and Fourier transform of some common signals. Now we are going to study the properties of Fourier transform. Not all the properties, we will be reviewing a few properties that we will be using in the preceding topics. So the first property is the linearity property. Linearity, we always already know that it says that if the input is scaled by a factor, for example, k, the output is also scaled by a factor of k. So if linearity exists in Fourier transform, it would mean that if we multiply the signal with, for example, some number a, then its spectrum or its Fourier transform will also be multiplied with the number a. So let's see if we multiply our signal by a scaling factor a, my signal becomes axt, and the Fourier transform will simply the signal, that is axt into e minus j omega t dt, which is the definition of the Fourier transform. Now as a is a constant, it may get out, एक जो है वो t के हिसाब से क्योंकि चेंज नहीं हो रहा, आप इसको बाहर निकाल सकते हैं, and left this thing is now nothing but the equation of Fourier transform. So what does it mean? It becomes a into x omega. So if we scale the input signal by a, then the output, that is the spectrum, is also scaled by a. So the Fourier transform is linear. Now we move to the time shift property. We want to see that if we shift the signal in time domain, what would happen to its spectrum. This is the final result to which we will move to. Okay, if we have a transform pair which is xt, and it has a transform pair with x omega. Okay, then if the time shift property tells us that if we shift the signal by a time t naught, what would happen, जो उसका ओरिजिनल स्पेक्ट्रम था सिग्नल का x ओमेगा वो मौजूद रहेगा, that would be multiplied by a phase angle minus ओमेगा t naught. दूसरे लफ्जों में उसके मैग्नीट्यूड स्पेक्ट्रम पर कोई फर्क नहीं पड़ेगा, उसका जो फेज स्पेक्ट्रम है उसमें माइनस ओमेगा टी नॉट का डिफरेंस आ जाएगा. ठीक है, so let's try to prove it. What we have done here, it's very simple calculus one things. So we assume that this t minus t naught is equal to t dash. Then if we differentiate it with respect to t, then dt dash by dt, इसका डिफरेंशियल 1 हो जाएगा और इसका डिफरेंशियल 0 हो जाएगा. So it means that if we cross multiply, it is dt dash is equal to dt. Okay, so if we want to calculate the Fourier transform, we want to obtain the Fourier transform of the signal that is shifted by a time of t naught. What we are going to do, हम Fourier transform की equation में x t minus t naught put कर रहे हैं. Now we know that t minus t naught is equal to t dash, so we replace t minus t naught with t dash, but then t is also replaced with t dash plus t naught. Okay, t dash plus t naught. So this is the result. Now we can see here this thing and this thing. Because it's linear, we can rearrange. We can just take this thing out here, and the remaining equation, this is the equation for Fourier transform. The only thing is that t is now replaced with t dash, but it is still the Fourier transform. So what we got, if we shift signal by a time t naught, the spectrum is multiplied with a factor e minus j omega t naught. In other words, we can say that there will be a change in its phase spectrum. Okay, then the frequency shift property. As I told you that we will not be discussing all the properties. So this is frequency shift property, which is the dual of time shift property. So I'm not going to discuss in detail. You can just have one-to-one mapping here. That if we shift the spectrum of a signal, that is, we are doing something in frequency domain. What's going to happen? In time domain, the signal is multiplied by a function ej omega naught t. Now we will be using these things that we have just reviewed to get to a very interesting conclusion. Suppose we have a constant function in time domain. That is, this is t, right? And this is x. X is a function of t, and we have a constant DC value for infinite time. So if it's from minus infinity to infinity, and if we are going to apply the Fourier transform formula, it is not going to work because this function is not bounded and it will result in infinite number. But using the properties of Fourier transform, we can obtain the spectrum of this DC signal as well. So from where we start, we will be starting from an impulse in frequency domain. We have an impulse, and this impulse is in frequency domain, so we can say this is del omega, and its location is 0 because we don't have any omega naught in this equation. And we want to calculate its inverse Fourier transform. We want to obtain its inverse Fourier transform. So what is the formula for inverse Fourier transform? 1 upon 2 pi minus infinity to infinity x omega g e j omega t d omega. So we put del omega in place of x omega and apply the property of impulse function. This whole integral is equal to 1. So we have 1 upon 2 pi. That is the inverse transform of an impulse function is a constant number with a magnitude 1 over 2 pi. So if we have this thing, okay, so if we just cross multiply, it means that a DC value of 1 will have a Fourier transform, or will have a spectrum of an impulse located at omega is equal to 0, which should be the location because it is DC, so it should not have any frequency, and the weight of this impulse is 2 pi. Okay, now we will apply some more properties to get to some more very interesting results. Now, if we apply the frequency shifting property, अगर हम इस impulse को move कर देते हैं, for example, left side पर, इसको हम 2 pi del omega plus omega naught बना देते हैं. Left shift किया कितना? By a factor omega naught. Then frequency shift property tells us that we will get e minus j omega naught t. Okay, and likewise, if we shift it from to left, that is omega minus omega naught, then we will get ej omega naught t. Now we know that Fourier transform is linear, so what we can do, we can add these two equations. So we have a transform pair in which we have two complex exponential which are complex conjugates of each other, and their Fourier transform is 2 pi del omega minus omega naught, that is one impulse at frequency omega naught and another impulse at frequency minus omega naught, and the weight of both these impulses is 2 pi. Okay, this is 0. Now why this is important? This is important because we can just convert it to a cosine wave, and cosine wave has a Fourier spectrum or Fourier transform pi del omega minus omega naught plus pi del omega plus omega naught. But we know that cosine wave, or even these pair of complex exponentials, the complex conjugates of each other, they are periodic signal, and for periodic signal we have Fourier series, we don't have Fourier transform. But the application of these properties tells us that we can obtain the Fourier transform of a cosine wave or even a sine wave or these complex conjugate pairs of complex exponentials. Okay, so what does it mean? इससे हम क्या कर सकते हैं, क्या फायदा उठा सकते हैं? देखिए, बात यह है कि when we obtain the Fourier series, हमें सिस्टम के सिग्नल के स्पेक्ट्रल कंपोनेंट्स का पता लग जाता है, लेकिन हमारी जो इक्वेशन होती है वो टाइम डोमेन में ही होती है, वो अभी तक फ्रीक्वेंसी डोमेन में नहीं गई होती. ठीक है? But when we are talking about Fourier transform of an aperiodic signal, then Fourier transform में जो हमारी इक्वेशन आती है वो टोटली फ्रीक्वेंसी डोमेन में होती है, वो टाइम डोमेन में नहीं होती. So there is a mismatch. लेकिन अगर आप गौर करें, हम फोरियर सीरीज में कर क्या रहे होते हैं, हम जो C0, C1, C2, C3 निकाल रहे होते हैं, all these are actually conjugates, coefficients of these type of complex exponentials. When we say, actually it is E, J, K, omega naught, T. So when we say C1, it means we have taken k is equal to 1, and we are talking about the coefficient of ej omega naught t. And when we say C2, it means we have put the value of k as 2, so we are talking about the coefficient of e power j 2 omega naught t. Okay. So in Fourier series, we are not doing anything but calculating the coefficients Ck of these complex exponentials. And now by applying these properties of Fourier transform, we know that this thing can be transformed into frequency domain. We are going to have an impulse, okay, with weight omega, weight pi. ठीक है जी. तो इसका मतलब हम पीरियोडिक सिग्नल्स के भी फोरियर ट्रांसफॉर्म कैलकुलेट कर सकते हैं. इससे एक यूनिफॉर्मिटी आ जाती है कि ओके, पीरियोडिक सिग्नल के स्पेक्ट्रम की बात भी हम फ्रीक्वेंसी डोमेन में कर रहे हैं और ए पीरियोडिक सिग्नल के स्पेक्ट्रम की बात भी हम फ्रीक्वेंसी डोमेन में कर रहे हैं. So what is the conclusion? The conclusion is that we can obtain the Fourier transform of any periodic signal by first obtaining its Fourier series and then multiplying each coefficient with an impulse of weight pi and location k omega naught. ओके, बात कुछ समझ में नहीं आई, ठीक है, कोई बात नहीं, हम अभी रिव्यू करते हैं इन सारी चीजों को और इस रिव्यू में इंशाल्लाह ये बात समझ में आ जाएगी. सो लेट्स सी इट point by point. The first thing, a spectrum of an aperiodic signal is obtained by using the analysis equation of Fourier transform. This is the analysis equation and we are very much familiar with it. Now the next thing, analysis equation takes us from time domain to frequency domain. We all know that. Now, synthesis equation of Fourier transform, or as it is said, inverse Fourier transform, takes us back from frequency domain to time domain. अब आप frequency domain में आ चुके हैं, आपको वापस time domain में जा रहा है, आप inverse Fourier transform यूज करेंगे जिसको आप synthesis equation of Fourier transform भी कहते हैं और इसकी ये इक्वेशन है. इस इक्वेशन को आज हमने ज्यादा यूज नहीं किया है, सिर्फ जो इम्पल्स इन फ्रीक्वेंसी डोमेन थी उसका टाइम सिग्नल निकालने के लिए इसको आज यूज हमने किया था आज की क्लास में. Then the periodic signal. The periodic signals spectral information can be obtained by using the analysis equation of Fourier series. आपके पास दो इक्वेशंस हैं Fourier series की, एक DC कंपोनेंट के लिए और एक AC कंपोनेंट के लिए, ठीक है. ये एनालिसिस इक्वेशंस ऑफ फोरियर ट्रांसफॉर्म्स फोरियर सीरीज हैं पीरियोडिक सिग्नल्स के लिए. इससे हमें स्पेक्ट्रल इंफॉर्मेशन पता लग जाती है कि इसमें कौन कौन सी फ्रीक्वेंसी मौजूद है. लेकिन जो बात अभी मैंने की थी, yet the final result is written in time domain. कैसे? Let's see. This is how we represent Fourier series. This is called the synthesis equation as well. कि आपके पास सारे हार्मोनिक्स हैं, k is equal to minus infinity to infinity, that is k1 भी होगा, -1 भी होगा, k2 भी होगा, -2 भी होगा, k3 भी होगा, -3 भी होगा. What does it mean? कि आपके पास ये पेयर्स आ रहे होंगे इन्फिनिटी तक, बीच में एक वैल्यू c0 की भी आएगी जो कि डीसी कोफिशिएंट होता है, ठीक है. लेकिन आप देख लें ये एक टाइम डोमेन इक्वेशन है. अब मैं इसका फोरियर ट्रांसफॉर्म निकालना चाहता हूं, तो अगर मैं इसका फोरियर ट्रांसफॉर्म निकालूंगा तो मैं फ्रीक्वेंसी डोमेन में चला जाऊंगा, ठीक है. तो आपने पहले फोरियर सीरीज निकाल ली है और फोरियर सीरीज की शक्ल में आपके पास अभी भी टाइम इक्वेशन मौजूद है. इंफॉर्मेशन फ्रीक्वेंसी की है बट इट इज इन टाइम डोमेन. सो अब मैं उसको फ्रीक्वेंसी डोमेन में मूव कर रहा हूं, कुछ नहीं करना, जस्ट अप्लाई फोरियर ट्रांसफॉर्म. नाउ वी नो दैट we have these complex exponential for k is equal to 1 and -1, 1 and -1. तो इनके लिए दो impulses हमें मिल जाएंगी स्पेक्ट्रम में. फिर 2 and -2, उनके लिए हमें दो impulses मिल जाएंगी, एक ओमेगा क्या कहते हैं 2 ओमेगा नॉट पर, एक -2 ओमेगा नॉट पर. फिर 3 और -3 हमें दो मजीद impulses मिल जाएंगी, एक 3 ओमेगा नॉट पर, एक -3 ओमेगा नॉट पर, एंड सो ऑन. और जहां तक बात आती है सी नॉट की, तो हमें सी नॉट तो पता ही है कि वो बराबर होता है 1/t नॉट के. तो उसका भी आप सिंपल एक कांस्टेंट का जब फोरियर ट्रांसफॉर्म निकालेंगे तो कांस्टेंट का फोरियर ट्रांसफॉर्म अभी थोड़ी देर पहले हमने देखा. व्हाट वाज इट? इट वाज an impulse at omega is equal to 0. So this is how we obtain the Fourier transform or spectrum of a periodic signal. पहले हम उसकी Fourier series निकालते हैं और फिर उस Fourier series का Fourier transform कैसे कैलकुलेट करते हैं? By using this property of Fourier transform. और ये प्रॉपर्टी खुद कहां से आई थी? इसके लिए हमने टाइम शिफ्टिंग, फ्रीक्वेंसी शिफ्टिंग और डुअलिटी सब यूज करते हुए हम यहां तक पहुंचे थे, ठीक है जी. तो